Plans and specifications. An architect or electrical engineer prepares a set of drawings that shows the necessary instructions and details needed by the skilled workers who are to build the structure. These are referred to as plans, prints, blueprints, drawings, construction drawings, or working drawings. The sizes, quantities, and locations of the materials required and the construction features of the structural members are shown at a glance. These details of construction must be studied and interpreted by each skilled construction craftsperson, mason, carpenters, electricians, and others before the actual work is started. The electrician must be able to, one, convert the two-dimensional plans into an actual electrical installation, and two, visualize the many different views of the plans and coordinate them into a three-dimensional picture as shown in Figure 2-1. The ability to visualize an accurate three-dimensional picture requires a throughout knowledge of blueprint reading, because all of the skilled trades use a common set of plans. The electrician must be able to interpret the lines and symbols that refer to the electrical installation, and also those used by the other construction trades. The electrician must know the structural makeup of the building and the construction materials to be used. Plans might be black line prints, which are simply photocopies. Diazo prints, referred to as white line prints, or computer-aided drawings, CAD, which are most commonly used today. The need for the drafter who used squares, triangles, curves with pen or pencil on paper has for the most part become history. We now need CAD technicians and engineers. Today's high-tech computers and wide-frame printers allow for storage and backup of clear and concise drawings, standardization of lines and symbols, easy of making revisions, the ability to zoom in and out when viewed on a monitor, simplicity of printing, black or color, and in many cases, the ability to view the structure in 2D or 3D. Turn a drawing to any angle and view the more complicated plans in layers. The larger the job, the greater the need for more detail. Although blueprints, for the most part, have gone the way of the dinosaur, they are still around. Electricians who have practiced this trade for decades are familiar with blueprints. Those of you recently entering the trade will probably not see blueprints on the job you work on. Blueprints were created by running yellowish, light-sensitive paper and transparent mylar with black images on it through a blueprint machine, where the two sheets are exposed to a bright light for a short period of time. The light-sensitive paper turns white in all places except where the black images are. Where the black images are, the light-sensitive paper turns blue. That is why it is called a blueprint. A tear-out, fold-out set of full-size plans for the residence referred to throughout this text is included in the back of the book. A few of the more common sizes for construction drawings are size C, size B, and size E. Specifications. Working drawings are usually complex because of the amount of information that must be included to prevent confusing detail. It is standard practice to include with each set of plans a set of detailed written specifications prepared for the architect. These specifications provide general information to be used by all trades involved in the construction. In addition, specialized information is given for the individual trades. The specifications include information on the sizes, the type, and the desired quality of the standard parts to be used in the structure. Typical specifications include a section on general clauses and conditions, which is applicable to all trades involved in the construction. This section is followed by detailed requirements for the various trades: excavating, masonry, carpentry, plumbing, heating, electrical work, painting, and others. In the electrical specifications, the listing of the standard electrical parts and supplies frequently includes the manufacturer's names and the catalog numbers of the specified items. Such information ensures that these items are of the correct size, type, and electrical rating, and that the quality meets a certain standard. To allow for the possibility that the contractor will not always be able to obtain the specific item, the phrase or equivalent is usually added after the manufacturer's name and catalog number. The specifications are also useful to the electrical contractor in that all of the items needed for a specific job are grouped together, and the type of size of each item is indicated. This information allows the contractor to prepare an accurate cost estimate without having to find all of the data on the plans. If there is a difference between the plans and specifications, the specifications will take preference. The electrical contractor or electrician should discuss any discrepancies with the homeowner, architect, and engineer. The cost of the installation might vary considerably because of the differences. So obtain any changes to the plans or specifications in writing. These are referred to as change orders. The specifications, specs for short, for the electrical work indicated on the plans for the residents discussed throughout this text are found in the back of the book in Appendix A. And NEC, how many words unique to the electrical trade? Terms unique to the NEC are defined in Article 100 per the NC Style Manual. A device is a unit of electrical system other than a conductor that carries or controls electrical energy as its principal function. An outlet is the A point on the wiring system at which current is taken to supply utilization equipment. A receptacle is a contact device installed at the outlet for the connection of an attachment plug or for the direct connection of listed and labeled electrical utilization equipment designed to mate with the corresponding contact device. A single receptacle is a single contact device with no other contact device on the same yoke or strap. A multiple receptacle is two or more contact devices on the same yoke or strap. A receptacle outlet is an outlet where one or more receptacles are installed. A lighting outlet is an outlet intended for the direct connection of a lamp holder or luminaire. A split wired receptacle is an electrician's jargon, not an official NSC definition. Electricians are very creative in their use of terms. Other terms for the use of these receptacles include split receptacle, split wired, split switch receptacle, and half switch receptacle. Figure 2-2, where a receptacle is connected to the branch circuit wires, the outlet is called a receptacle. When a luminaire or lighting fixture is connected to the branch circuit wires, the outlet is called a lighting outlet. To create a split wired receptacle, simply remove the tab between the two hot terminals. Typically, this is done for switch receptacles, but can also be done for multiple branch circuits. When a luminaire lighting fixture is connected to the branch circuit wires, the outlet is called a lighting outlet. To convert a conventional duplex receptacle into a split wired receptacle, simply remove the tab between the two underground conductor terminals, brass colored. See figure 2-4. The receptacle can then be used where one receptacle is hot at all times and the other receptacle is switch controlled. By definition, toggle switches, receptacles, circuit breakers, fuses, and occupancy sensors are devices because they carry or control current as their principal function. The term opening is widely used by electricians and electrical contractors when estimating the cost of an installation. The term opening covers all lighting outlets, receptacle outlets, junction boxes, switches, and so forth. The electrician and or electrical contractor estimates a job at X dollars per lighting outlet, X dollars per switch, X dollars per receptacle outlet, and so on. These estimates include the time and material needed to complete the job, plus an anticipated profit. Each time of electrical opening is represented on the electrical plans as a symbol. The electrical openings in Figure 2-5 are shown by the symbols Figure 2-6. Electrical symbols. Electrical symbols used on an architectural plan show the location and type of electrical device required. A few electrical symbols for a typical electrical installation as taken from a plan are shown in Figure 2-5. Note that generally lines that represent electrical wiring are curved in shape to reduce confusion. Wait, are shown in figure to generally lines that represent electrical wiring are curved in shape to reduce confusion with structural components. The National Electrical Contractors Association recently revised their standard entitled Symbols for Electrical Construction Drawings. This document is an American National Standards Institute, ANSI standard. Figures 2/7 throughout 2-12 show the electrical symbols more commonly found on architectural and electrical plans. Because some architects or engineers may use different symbols to represent an outlet, device, or control scheme, it is important to check the plans and specifications of any job you are working on for a symbol, schedule, or a legend to make sure you have interpret interpreted the symbols correctly. The curved lines in Figure 2-5 run from the outlet to the switch or switches that control the outlet. Curved lines are used to differentiate the electrical circuitry from the building construction drawing lines. Several drawings show a curved line between 3-way and 4-way switches to indicate the control points. Some receptacles have one half of the duplex switch. A curved line runs from the receptacle to the switch or control point. Other curved lines show the connection of luminaires or the circuiting for receptacles. A study of the plans for the single family dwelling shows that many different electrical symbols are used to represent the electrical devices and equipment used in the building. Be very careful when interpreting symbols because of the similarity between them, as shown in Figure 2-13. For example, the left symbol can be used for a split wired or a half switch duplex receptacle. Several of the rooms in this dwelling have duplex receptacles with half of the receptacle switched and the other half remaining hot or energized all the time. Table or floor lamps can be plugged into the receptacle that is switched to allow control of room lighting from near the door. The receptacle remains hot all the time for any appliance or fixture that is to remain energized at all times. In some areas, the receptacles are referred to as switch receptacles or split wired receptacles. The concept of split wire receptacles sometimes includes using branch circuit wiring, often a cable. Often a cable type wiring method. with two hot energized conductors and a common neutral. For both applications mentioned here, the tab is removed on the side of the duplex receptacle so that each receptacle can be controlled separately or have both undergrounded conductors connected to it. This switching arrangement satisfies NEC, exception number one, which permits switch controls receptacle to serve as the lighting outlet in the habitable rooms other than kitchens, laundry areas, and bathrooms. The architect uses symbols and notations to simplify the drawing and presentation of information concerning electrical devices, appliances, and equipment. A Nation is generally found on the plan's blueprints next to the specific symbol, calling attention to a variation, type, size, quantity, or other necessary information. In reality, a symbol might be considered to be a notation because symbols represent words, phrases, numbers, quantities, and so on. Another method of using notations to avoid cluttering up a blueprint is to provide a system of symbols that refer to a specific table. For example, the written sentences on plans could be included in a table referred to by a notation. Figure 212 on page 40 is an example of how this could be done. The special symbols that refer to the table would have been shown on the actual plan. The notation for the receptacle shown at the right in figure 2-13 indicates the receptacle is to be in an enclosure suitable for a weatherproof location. When preparing electrical plans for commercial and industrial buildings, most architects and electrical engineers use symbols approved by ANSI wherever possible. For residential projects, usually only the basic symbols are used, showing the location of receptacles, switches, and appliances, and luminaires. Specific circuitry, as shown in Figure 2-10, may be provided by the architect or engineer, may be left to the electrician to show on the plans. Later in this text, you will find suggested cable layouts for all of the branch circuits in this residence. These cable layouts show the required number of conductors between outlets and switches. Luminaires and outlets. The term luminaire is found in the NEC. In the United States, we previously used the term lighting fixture for years, but because the NEC is an international code, we must become familiar with some new terms such as luminaire. By definition, a luminaire is a complete lighting unit consists of a light source, such as a lamp or lamps, together with the parts designed to power, position the light source and connect it to the power supply. It may also include parts to protect the light source, ballast, and distribute the light. A lamp holder itself is not a luminaire. Simply stated for our purposes, a luminaire and a lighting fixture are one and the same. The location of lighting outlets is determined by the amount of type of illumination required to provide the desired lighting effects. It is not the intent of this text to describe how proper and adequate lighting is determined. Rather, the text covers the proper methods of installing the circuits for such lighting. Luminaire manufacturers publish catalogs that provide a tremendous amount of information regarding recommendations for residential lighting. These publications are available at electrical distributors, lighting showrooms, and home centers. Architects or owners often include a specific amount of money in the specifications, referred to as a fixture allowance. Electrical contractors include this amount in their bid, and the choice of luminaires is then left to the homeowners. If the owner selects luminaires whose total cost exceeds the fixture allowance, the owner is expected to pay the difference between the actual cost and the fixture allowance. The electrician needs to know the details of the luminaire to be installed so that a box designed for the size and weight of the luminaire can be positioned correctly. Figure 2-14 shows several types of boxes that may be appropriate depending on the size and weight of the luminaire. How luminaires are handled varies by job and geographical area. Sometimes the received luminaire housings are included in the base bid, and the trims are included in the fixture allowance. Always read the specifications and study the plans carefully for important symbols and notations that might reference luminaires. Surface-mounted luminaires are secured to an outlet box, a raised plaster adapter ring, or a device box using the mounting hardware, straps in number 8-32 or number 6-32 screws. Furnished with the luminaire. Some outlet box hangers assemblies have a fixture stud in which to fasten the luminaire. Symbols used to represent lighting outlets and switches. Typical lighting outlet symbols are shown in figure 2-14. Typical switch symbols are shown in figure 2-15. Outlet device and junction boxes. NEC Article 314 contains much detail about outlet boxes, device boxes, pull boxes, junction boxes, and conduit boxes, LBRLC, etc., all of which are used to provide the necessary space for making electrical connections, to contain wiring and to support luminaires and so on. NEC Article 314 is quite lengthy. For the moment, we will focus on some of the basic code requirements for outlet boxes, device boxes, and junction boxes. Additional code requirements are covered on as needed basis in this chapter and in later chapters. Screw sizes for typical electrical boxes are as follows: device boxes and faceplates, outlet boxes, ceiling suspended paddle fan boxes, 2 sets of holes. The numbers 6, 8, and 10 refer to the diameter of the screw, with the smaller numbers being a smaller diameter. The larger number 32 refers to the number of threads per inch or the pitch of the thread. For these threads per inch or the pitch of the thread. For these screws and similar screws are coarse and fine thread is established according to the Unified Thread Standard, UTS. Coarse and fine do not refer to the quality of the thread or to the number of threads per inch. Dimensions and threads for these screws are shown in the following table. Electricians commonly carry a multi-tap tool to clean out threaded holes that may have become damaged or filled with paint or other contaminants. Some basic NC requirements. Securely mounting. Boxes must be securely mounted and fastened in place. Wooden braces must not be smaller than 1 inch times 2 inch, 25 millimeter times 50 millimeter. It must be treated if installed in wet locations. Several figures in this chapter shows methods of securing outlet boxes to the structural members of the building or structure. Box or conduit body required. With conduit, electrical metallic tubing, non-metallic sheath cable, type MC cable, or other cables are installed. A box or conduit body must generally be installed at each conductor splice connection point, outlet point, switch point, junction point, pull point, or wiring method transition point. This requirement is illustrated in Figure 216. A box or fitting must be installed wherever there are splices, outlets, switches, and other junction points as indicated by the OK. Some luminaires, such as resist luminaires marked OK, have integral junction boxes. Wiring luminaires without an outlet box, such as marked No as not permitted. Alternatives to this general rule can be found in 300.15 through L. Typical exceptions are surface-mounted strip luminaires, as shown in Figure 2-2. Most of these have a back plate that has a trade size 1/2 knockout intended for the direct entry of a cable without the need for a box behind the luminaire. This is permitted by 300.15d because the luminaire has an integral wiring compartment protection. Where cables enter or exit from a conduit or tubing that is used to provide cable support or protection against physical damage, often referred to as sleeving the cable. However, a fitting must be provided on the ends of the conduit or tubing to protect the cable from abrasion. This is not to be confused with transitioning between two wiring methods, which is also allowed without a box or conduit body 300.15F, as long as a fitting is provided to join the two wiring methods together and the conductors are not spliced within the fitting. Figure 2-17 shows a wiring method transition point from a cable type wiring method to a raceway. Size of boxes must be large enough for all of the enclosed conductors and wiring devices. Installing boxes too small for the number of conductors, wiring devices, luminaire studs, and splices is a real problem. NEC 300.15F permits a transition to be made from one wiring method to another wiring method without a box. In this case, the armor of the type MC cable is removed, allowing sufficient length of the conductors to be run through the EMT. A proper fitting must be used at a transition point, and the fitting must be accessible after installation unless listed for concealed installation. The conductors in type MC cable are often THHN insulation. Number of conductors in box. NEC dictates that outlet boxes, switch boxes, and device boxes should be large enough to provide ample room for the wires in that box without having to jam or crowd the wires into the box. Jamming the wires into the box can not only damage the insulation on the wires, but can also result in heat buildup in the box that can further damage the insulation and the wires. The code specifies the maximum number of conductors allowed in standard metal outlet device and junction boxes. The metal boxes included in Table 314 are considered standard boxes. These boxes are manufactured in the dimensions that are given in the table. The manufacturer of these standard boxes is not required to mark the volume of the box unless it is produced in a non-standard size. Non-metallic boxes are produced in a non-standard sizes and are required to be marked by the manufacturer with their cubic inch capacity. When conductors are all the same size, the proper metal box size can be selected by referring to Table 314. When conductors in standard boxes are different sizes and non-metallic boxes are installed, refer to Table 314 for specific volume allowances needed in the box based on the size of the conductors in the box. The total cubic inch volume needed for the particular size of wire being used, plus additional space needed for wiring devices, clamps, and so forth can be determined by adding the appropriate number of volume allowances required by 314. We will work out a few examples. Table 314 does not take into consideration the space occupied in the box by items like luminaire studs, cable clamps, terminal blocks, switches, pilot lights, and receptacles that may be in the box. These require additional space. Table 2-1 shows the additional conductor volume allowances that must be considered for different situations. When using a non-metallic box and all conductors are the same size, non-metallic boxes are typically stamped with the internal volume of the box. Let's look at an example. A non-metallic box is marked as having a volume of 22.8 inch, and the box contains no luminaire stud or cable clamps. How many 14 AWG conductors are permitted in this box? From Table 314, the volume requirement for each 14 AWG conductor is 2 inch. Therefore, the maximum number of 14 AWG conductors permitted in this box is um, when using a metal device box and all conductors are the same size, a box contains one wiring device and two internal cable clamps. The wiring methods are two 12-2 NM cables with equipment grounding conductors. 4 12 AWG conductors, each conductor counts once. One wiring device counts as two conductors, two cable clamps only count one, two 12 AWG equipment grounding conductors only count one. When using a metal or non-metallic box and the conductors are different sizes, what is the minimum cubic inch volume required for a box that will contain two internal cable clamps, one switch and one receptacle, each mounted on a separate yoke or mounting strap? One 14-2 MC and one 12-2 type MC cables are used. Each cable contains an equipment grounding conductor that is the same size as the circuit conductor in that cable. Select a metal box and a combination of box, plaster ring. This might consist of a square or deeper box with a two gang plaster ring or two device boxes that are ganged together. Any other metal box or combination that provides not less than 22 inches area can be used. Recall that the volume of the plaster ring that has its volume mark can be added to the volume of the box. For non-metallic boxes, select a two-gang box that is marked with a volume not less than 22 inches. Section 314 requires that box with internal volumes of 100 inch or less, other than those listed in Table 314, be durably and legibly marked by the manufacturer with their cubic inch capacity. Non-metallic boxes have their cubic inch volume marked on the box. When sectional boxes are ganged together, the calculated volume is at the total cubic inch volume of the assembled boxes. When installing a box that will have a raised cover attached to it, when marked with their cubic inch volume, the additional space provided by plasterings, dome covers, raised covers, and extension ring is permitted to be used when determining the overall volume. This is illustrated in figures 2-19 and 2-20. How many 12 AWG conductors are permitted in a 4 times 1/2 inch square box with a plaster ring marked with a volume of 4.5 inch? Refer to figure 220 in table 314. We will find the 4-inch square box. Deep has a volume. At the volume, um, this calculation actually resulted in 11.33 conductors. The conductors field numbers in table 3.14.16 were created by dropping an excess above the whole number after the calculations were made, following the same procedure. This conductor field calculation dropped off the axis. Electricians and electrical inspectors have become very aware of the fact that GFCI receptacles, dimmers, and timers take up a lot more space than regular wiring devices. Therefore, it is a good practice to install boxes that will provide a plenty of room for the wires, instead of pushing, jamming, and crowding the wires into the box. Figure 2-21 shows that transformer leads 18 AWG or larger must be counted when selecting a proper size box. The minimum required size of equipment grounding conductors is shown in table 250.122. The equipment grounding conductors are typically the same size as the circuit conductors and cables, having 14 AWG, 12 AWG, and 10 AWG circuit conductors. Thus, for normal house wiring, metal box sizes can be calculated using table 3.14.16. Refer to figure 2-18. Figure 2-18, a quick check box selection guide, shows some of the most popular types of boxes used in residential wiring. This guide also shows the box's cubic inch value. Figure 2-23 illustrates typical wiring using cable or wiring conduit. Note in this figure how the conductor count is determined. Using an electrical metallic tubing (EMT) makes it possible to loop conductors throughout the box, which count as one conductor only, provided the loops are shorter 12-inch, or as provided in 300.14 C314.16. Looping conductors through a box is not possible when using a cable as the wiring method. The basic rules for box fill and summarized in Table 2-1. Boxes that are intended to support ceiling paddle fans are discussed in detail in Chapter 9. Securing cables to boxes. If the conditions of the exception are complied with, multiple type NWU cables are permitted to enter through a single knockout opening in a non-metallic box. See figure 2-24. This permission is not given for metallic boxes. However, cerebral connectors for non-metallic cables and type MC cables are rated to connect two cables to a knockout in a metal outlet box or other similar enclosure. Transformer leads 18 AWG or larger must be counted when selected the proper size box. In the example shown, the box contains 4 conductors. When marked with their cubic inch volume, the volume of the cover may be added to the volume of the box to determine the total cubic inch volume. The push-in cable connector shown in figure 2-25 is rated to connect multiple type NW cables in a single knockout, as shown in the figure. The connector is also rated to connect a broader range of cable sizes. It can be inserted from either outside or inside the box, with it being suitable to be inserted from inside a box. It is very well suited for old work installations where a metal box desired or required. Flush-mounted installations states that were non-combustible surface material is used on walls or ceilings, then boxes, plaster rings, doom covers, extension rings, or listed extenders must be mounted so that they will be set back not more than 1/2 inch from the face of the surface material. Where combustible surface material, wood paneling is used on walls or ceilings, boxes, plaster rings, dome covers, extension rings, or listed extenders must be set flush with the surface material. These requirements seek to prevent a fire from being started by arcing at a loose connection, a short circuit, or a ground fault that might occur within the box. This significantly reduces the supply of oxygen needed to keep a fire burning. Closing the gaps around boxes further reduces the spread of fire. Box position requirements in walls and ceilings constructed are various materials. If the box is not flush with the finished surface as a result of improper installation, or if paneling, drywall, tile, or a mirror is added, then install a box extender, sometimes referred to as a code saver. One type is shown in C. Switch device boxes installed between studs using metal switch box supports, often referred to as cruise strips. If wood strips are used, they may have a cross-sectional dimension are not less than 1 inch times 2 inch. Yang sectional switch devices boxes can be installed using a pair of metal mounting strips. These strips are also used to install a switch box between wall studs, figure 2-27. When an outlet is mounted at a specific location between joists and for ceiling mounted luminaires, an adjustable bar hanger is used, as in figure 2-14. Surface extensions. A surface extension from a box of a concealed wiring system is made by mounting and mechanically securing an extension ring over the concealed box. An extension ring is the same dimensions as an outlet box, but without a back or bottom side. It is designed to be secured to the concealed box. An exception to this is that a surface extension is permitted to be made from the cover of a concealed box. If the cover is designed so it is unlikely to fall off or be removed, if its securing means become loose, the wiring method must then be flexible for an approved length and permit removal of the cover and provide access to the box interior. See figure 2-29. It must be arranged so that any required grounding continuity is independent of the connection between the box and cover. This is shown in figure 2-29. Depth of boxes. Outlet and device boxes are required to be on an approved depth so that conductors will not be damaged when installing the wiring device or equipment into the box. Merely calculating and providing the proper volume of a box is not always enough. The volume calculation might provide adequate, yet the size, depth of the wiring device or equipment might be such that conductors behind it may be damaged. The general rule is that outlet and device boxes that enclose devices or utilization equipment are required to have a minimum internal depth that accommodates the rearward projection of the equipment and the size of the conductors that supply the equipment, without any other specific requirements. This rule should be adequate for sizing the box. However, you may not know how the wiring device will be at the time of rough in. Paying a little extra for boxes that are deeper at the time of rough in will pay big dividends when finished operations are performed. For large equipment, described as equipment that projects more than 1/78 inch rearward, boxes are required to have the depth of the equipment plus 1/4 inch. Boxes that enclose devices or utilization equipment that are supplied by a 12 or 10 AWG conductor are required to have an internal depth no less than 1/3/16 inch. If the device or equipment projects into the box by more than 1 inch, the depth of the box must be at least the depth of the device plus 1/4 inch. If the conductor is entered through the rear of the box, directly behind the equipment, the minimum depth must increase to the depth of the equipment plus 1/2 inch. It is it is good practice to install outlet or device boxes that are as deep as the construction will allow or that are available. Keep in mind that space must be allowed for making up conductors with pressure connectors, such as twist-on wire connectors or crime sleeves. These are usually pushed back into the back of the box after makeup. Space must be allowed for devices in front of the connection. Extra depth of the box must be provided in receptacles such as for the electrical ranges, electric clothes, dryers, GFCI receptacles, AFCI receptacles, time switches, and motion detectors. Width of box, watch out. Large wiring devices such as a 30 ampere 3-pole 4-wire dryer or a 50 ampere range receptacle will not fit into a single gang box that is 2 inches wide. These receptacles measure 2.10 inch, 53.3 millimeters in width.